What we'd like to do is talk a little bit about some of the research we've been doing at West Central Research and Outreach Center as part of a project that we call Greening of Agriculture. And basically this is just an overview of the picture of our research center at Morris, and Mike is going to go into a little bit more detail of what some of those buildings are and what kind of things we have going on there outside of the projects I'm going to talk about. The project that we have is kind of an overarching project at the center called the Greening of Agriculture. And basically, consumer supply chains are asking questions about the environmental impacts of all our ag production systems with an eye towards greenhouse gases, carbon footprint, all those kinds of things. You can argue, is it happening, is it not, so forth, so forth, but the consumers are asking about it. Market chains are starting to demand those things, so we're trying to generate data that would help producers respond to those challenges. Modern production uses a significant amount of fossil fuel resources in things like fertilizer, nitrogen fertilizers, crop protection products, diesel fuel, electricity, and so on. And basically our question is there a way we can reduce the reliance on those fossil fuels in a way that does not compromise production and may in some cases even enhance production if possible? So in this project, it's a multidisciplinary thing. Right now we have three prongs, dairy production and crop production, and swine production, all research programs at our research center out in Morris. And then we're incorporating this summer some algae production as a way to recapture nutrients out of wastewater and dairy and then feed those back to dairy calves and potentially pigs. And we're figuring out, trying to figure out how our horticulture program would fit into this overall project as well. So we're going to focus on swine today. And some of the approaches we're trying to use to reduce the carbon footprint, if you notice the title, it said one piece at a time. In my mind, or our minds, it's not going to be there's a silver bullet, we're going to make this one change, we're good on carbon footprint, greenhouse gases are down, we move on. It's going to be a lot of incremental things that all come together to drive that footprint down. And so today what I want to discuss a little bit is some monitoring we've done on commercial farms for the last 18 months. To try to understand where the power is being used. Some conservation practices, just a few that we've thought of and looked at. Some generation of renewable energy. Might this have some influence on pig performance in a positive way? And then finally wrap up with some life cycle analysis. So the first project, monitoring energy on farms. Basically what we're doing is monitoring the monthly electrical use in representative barns. We're recording electrical use in the barn, heating fuel in the barn, and the pig production. So basically, farmers know what they pay for power and heating fuel. But once it gets past the meter, where's that power going? How's it being used? Where are the places that there's the most opportunity for improvement? And as you're sitting there, you can go through your mind, and you probably come up with a few of which, oh, this is probably where we can save some power. Hopefully this data will reinforce what you're thinking and what we were thinking. So what we've done is, and I forgot to get them out of my bag, but we have this spaghetti junction of stuff in the power panels at commercial farms. And we've got the current sensor. It's basically a little clip that goes around the wires and measures the power running through those lines. And then we have a little logger out here that sticks on the side that here's one here, sticks on the side that records that data every 10 minutes or whatever, 24/7. Well, mostly 24/7. They fail at times, but so the idea was try to get representative power. So on a farrowing unit, we'd monitor all the circuits going into one room. 10 rooms in the farm. Say, okay, they're going to cycle through the rooms in a year, so we're going to take this room, multiply by 10, and then try to get some of the ancillary power for washers and dryers and shower, water heaters, and that kind of thing, to try to recreate where all the power is going. So we've done that on a farrow to wean unit, nursery units, and finishing units. So here's just a little bit of the breed to wean units. 2 farms. A little bit of a very brief description of the farms. Farm 2 has a gestation barn, curtain-sided sow barn, power ventilated. Here's the total power usage per month. 2,500 sows, production on an annual basis. They're using about 11.4 kilowatt hours per pig wean on that farm. Farm 6, Cross-ventilated gestation barn, typical farrowing room. They're using more power. It's a bigger unit, but bottom line, not terribly different in terms of the electricity use per weaned pig on that farm. If we look at where's that electricity going, 45% of the power on this is farm 2 went for heat lamps. And as you were thinking about before I showed you any data, if you said where's the power being used on a farrowing barn, I'm sure heat lamps would pop in your head. It popped in our mind, but we didn't expect it to be 45% of all the power going into that farm was on heat lamps. 27% was miscellaneous, so that's the employee quarters, the showers, clothes washers, that kind of thing. 21% is ventilation, and then a bunch of other miscellaneous things. We look at farm 6, same picture. Bigger farm, 46% of the power on heat lamps, and you see a very similar picture. So we felt pretty good that we have some consistency across at least these two units. Now what we did is we converted that electricity use to BTUs so we could throw in the heating fuel, propane, and we come up with this picture. So the gray here is heating propane. So in both farms, it's about half of the BTUs used on the farm on an annual basis is for heating the barn. The orange is heat lamps, and then the green is ventilation. So you see kind of a similar picture across these two farms. So we moved to the nursery, and two nurseries, very similar in their construction, design, and operation. A little difference in terms of size, number of pigs that are produced, but 2.3 kilowatt hours per pig produced, or a little over 2. And this is a 3-week weaning to 50-pound kind of production phase. So if we look at where the electricity is being used in this farms, ventilation comes up as a bigger portion of the power use. We had a little more problems with miscellaneous recording what those are. In all these farms, we were able to get enough circuits that we were actually measuring about between 65 and 80% of the power that's coming through the meters. We were accounting for on the back side of the meter. So we're doing a reasonably good job of figuring out where all this power is going. So this was nursery 3. If we look at the bigger nursery, nursery 7, a similar picture. We had a little bit more unaccounted for power and miscellaneous things because they had some other activities at that site. There's a incinerator there and some other things that we weren't quite measuring as quickly as much as we'd like to have. So when we look at that BTU use across the whole farm, the unit heating, not surprisingly, comes up as the biggest portion of taking care of those pigs in the nursery phase. And again, consistent across the two farms. We moved to finishing, a little bit different here. This barn was a tunnel ventilated barn, a 1,200 head farm, a little bit older barn. Excuse me, I'm backwards. This is tunnel ventilated, a newer barn. They were using about 15 kilowatt hours per pig finished coming through that farm. Farm 5 is the curtain-sided barn, an older barn, 1,200 head barn. They were using 3.1 kilowatt hours per pig. Basically, this was representing pit ventilation on that farm. And if you also note, the total kilowatts used per month, very different across the two farms. And if we look at where that distribution of electricity is used in those farms, about 50%, this is the tunnel vent barn, 50% in ventilation, some miscellaneous. We go to the curtain-sided barn. Ventilation uses a whole lot greater proportion of electricity, but it's much less total electricity, and basically this is the continuous pit fans running. There wasn't anything else really, feed lines and a few other miscellaneous things in this farm. So ventilation represented a larger portion. So if we look at it on a BTU basis, here heating was 40% in the tunnel vent barn, and 75% in the curtain-sided barn. And the difference here is this barn tended to bring pigs in a fair bit lighter, and so they're really pushing to try to keep those pigs warm and using a higher proportion in heating fuel. So that's kind of a real thumbnail sketch of where the power is going on these farms, and we looked at those things and said, now what can we do? Where can we intervene to try to improve the efficiency and maybe conserve some energy? So if we think about nurseries, which we honed in on that heat use in the nursery, and we did this project a few years ago, funded by Port Board, to look at a concept called reduced nocturnal temperature. Some of you have been around a few years. You remember Mike Brum and the Nebraska group looked at setting the temperature back at night. And basically the whole idea is we could probably reduce heating and fuel costs. Put this slide in just to admit to you all that we understand that the cost for heating and electricity in the total realm of pig production costs is pretty small. Few bucks, few percent. And so by making these changes, we're not maybe going to have huge economic benefits, but there is some savings that can be had. And if we think of these market pressures in terms of carbon footprint in that, we're thinking there might be advantages down the road. And if we think about these pigs, some work done here back in several years ago in Canada, if they let nursery pigs choose their temperature by being trained to hit a heat lamp, hit a button that would turn the heat lamp on, then they could lay under the heat lamp and kind of sun themselves, you know. So they got this immediate response of hitting the button, I get warmer temperatures. If you let the pigs self-select, this is from midnight to midnight. During the night, they choose a temperature about 24 degrees centigrade. And then as the day goes on, they choose a warmer temperature. And here's about 3.3 degrees centigrade, or about 7.5, 8 degrees Fahrenheit. So they're picking a warmer temperature during the day and a cooler temperature at night. So back in the day when Mike Brum and that group in Nebraska said, well, why don't we just set the temperature back at night because the pig wants it cool anyhow, and there should be fuel savings. Well, back in the 90s, this concept was conceived, but it didn't really get adopted because we didn't have the computerized controllers and all that to just automatically do it. And you know, on a farm, if you had to go in the morning and turn the temperature up and then remember to turn it down at night, and yeah, you know how that worked. So it didn't really get adopted very much. So we reevaluated that concept. We've got better nurseries, and these data came out. You all remember $7 propane that one winter? This data came out right ahead of the $7 propane. And it was like, we didn't plan it that way, or it just worked out. So, and we also know that the leaner pigs now, they generate more body heat. They're little heaters themselves in the barn, so why can't we take advantage of that heat? So basically, we ran a couple studies. I'm just going to show you the second study, where we used the reduced nocturnal temperature, and we did a very aggressive implementation of that, and said, well, does that affect pig performance? And what kind of fossil fuel savings could we have? So here's the cooperating universities, Ohio State, SDSU, and ourselves in Missouri. We're all part of this project. Basically, we had about a little over 4,000 pigs on the project. The trial was 28 to 42 days. Basically, every facility had 2 rooms, mirror images of each other. In one room, we would run the temperature normal, like you normally would manage, and the other we used the reduced nocturnal temperature. So in the control room, 86 degrees Fahrenheit at pig height, decrease 3.5 degrees Fahrenheit every week out through the 5 or 6 weeks of the nursery phase. In the R&T room was exactly the same as the control on days 1 to 4. We had to get the pigs in, get them on feed, get them settled, and then beginning on day 5, we would reduce the temperature 15 degrees Fahrenheit at night, at 7 o'clock at night. Automatically it would change that setting, and then at 7 o'clock in the morning, it would bring it back up to the daytime. So during the daytime, both these rooms were run exactly the same. But at night, the R&T room was targeting 15 degrees cooler than the control. So here's kind of a conceptual idea of how that temperature at 7 o'clock in the morning, it goes up, meets the control room during the day. 7 o'clock at night, we start to let the temperature drop to our new set point and then back up. So that's kind of the way it was designed. And here's an actual temperature graph of one of our rooms in Morris. The red line would be the control temperature in the room. The blue line is the R&T room. And you see, okay, here's the time where we kept it the same. And then beginning day 5, we dropped the temperature at night. And basically the way we do that was we just change the activation temperature for the heater. So we change that so that it's cooler. We don't want to change the new set point because as soon as you change the set point, all the fans come on and it drives that temperature down. Well, why exhaust all that heat that you just paid to put in there all afternoon? And so basically what happens is the minimum ventilation just keeps running and the room just gradually cools down until it hits the new set point, and then the heater starts kicking in to try to maintain that temperature. And that's what you see here is it drops pretty quickly, and it doesn't hit the bottom temperature until about 3 in the morning. So those pigs are generating heat. And then in the morning, the temperature comes back up. The other thing to see here is we get out here a ways, we never do get our 15-degree spread because those pigs are generating enough heat. We get out here, we had current sensors on the furnaces. We get out somewhere in here from 7 o'clock at night until 7 in the morning, the furnaces never ran. Okay? So that's the scenario we're under. Here's the performance. On the left side is the control room. The right side is the R&T room. Looks pretty similar to me. Average daily gain, feed intake, gain to feed, morbidity, mortality, exactly the same. The number of pigs we treated in each room, exactly the same. We look at the fuel savings. Here's heating fuel use. We've got a significant decline, and not so much, but still a decline in electricity use. And here's the 4 stations. And the reason this slide is in here, every single one, there's a significant reduction in the heating fuel use. So it was a consistent response everywhere we did it. The previous experiment we did, we had 4 stations in that. Same thing. It worked every time. I never done an experiment that it works every time. Okay? So we're pretty convinced of this. If you look at the cost savings, this is a figure in propane at $1.60, in power, electricity at 10 cents. The overall average was $1.73 per pig. This was Ohio. Ohio ran this in a commercial nursery. And these guys changed their management after this study. They were blowing a lot of heat out. They had their ventilation set wrong. And we're blowing a lot of heat out. So we got some good data from them, and we also saved them a fair bit of money in this experiment. So here's kind of the bottom line. A lot of math here. We can talk about the conversions. But bottom line on this experiment, we saved about 15.5 pounds of CO2 equivalent, greenhouse gases, per pig coming through that nursery. So not huge, but it's another piece that can help ratchet that emissions down. So the conclusions, at 15 degrees Fahrenheit, that setback starting at day 5, because we've got to get them on feed. And when you go in those nurseries, I go into nurseries at night after that temperature started to drop, you would look at it and you say, this is not right. Pigs are piling, it's all the things they shouldn't be. But the morbidity, mortality data and the performance data said it's probably not a problem. They were cold. But now, if you had a disease insult, you had Persy pigs or something, maybe you want to be a little more conservative with this. But these were all pretty good health pigs, good environment, no drafts. We were able to do that. I tell guys, producers that call and say, well, geez, that's a lot. Well, go 5 degrees, see how it works. Then kind of ease into it. Didn't influence performance. We've saved almost 30% in heating fuel and almost 20% in electricity across those 4 university studies. And then this carbon CO2 equivalent savings is also there. So now I'm going to shift gears. Another part of the Greening of Ag project is some energy generation. First one was, where's the power going? Then we talk a little bit about how can we conserve fossil fuels. Now can we maybe replace some of them with some energy generation? Mike's going to talk a little bit more about our solar project. This is our finishing barn at Morris. We got solar on the roof, 27 kilowatts of power, and the whole idea was, with the panels on the roof, power the barn underneath it. And so here's kind of an overall summary. Mike's going to talk a little bit more about the finances. The reason this chart is in here is basically the blue bars are the power use by month in that barn. We're also in the monitoring project monitoring our own barn. And we see the various in the summer, of course, you use more power, you're ventilating. It's a power ventilated barn, deep pitted. The black line here is January 2016. You remember that month? Lots of snow, lots of clouds. You see our power generation that day, that month, was basically zero. The snow was covering the solar panels, and we had cloudy days when it wasn't, and so that's something you've got to be aware of. And maybe an argument for having ground mounts instead of roof mounts. But Mike will get into that a little bit more. We also, in one of the finishing barns we were monitoring, this is the data from Finisher 4, and the shaded stuff in the back, that was their power usage over that year of 2015. And then these curves are modeling through using PV Watt, a publicly available software package, to predict what kind of power could be produced by panels. And we basically said, well, maybe it would make sense for him to put in a 48 kilowatt system to meet most of his needs, and then on this peak, buy off the grid to cover his needs there. Mike's going to talk a little bit more about the rationale behind this. So the other bit was, could we use renewable energy to even maybe enhance pig performance? And I put a question mark here because we don't have the data. I'm just going to tell you about a project that we've got planned for this summer. Basically, whenever I was doing another talk on some soil management stuff, I came across this work, a Korean work, that said, looking at the temperature of drinking water. And basically, as they looked at 72 degrees Fahrenheit down to 50 degrees, these brown line bar here is voluntary feed intake. These were sows were during lactation at about, I think they were like 85 or 86 degrees Fahrenheit is the housing situation. So they were heat stressed. You give them this cool water, got a pretty important increase in feed intake, and then also or water intake and feed intake. So in other words, keeping those sows cool with cool water made them eat more. And if you go a little further, I took that slide out, but if you also looked at respiration rates on those sows in the cool water dropped, and piglet gain went up. So the sows were more comfortable, they were eating better, they were milking better. So then I saw these data right about the time we were starting doing the monitoring on the sow farms. And so when Kirsten, our technician, went to download the data, I said, well, go through the barns, and we had a protocol of pick random crates in the farrowing barn and run water out of the nipple and capture that water and measure the temperature. Okay, it was highly technical the way she did it. Push the button, put a cup under it, and whenever all the water is full, and we used our swine behaviorist Yushi to tell us how long an average drinking bout for a sow would be. So we ran the water for, I forget exactly what the protocol was, 45 seconds or something like that. So we get the water that's coming out of the line. And here's the temperatures that she recorded from April of 15 through May of 16. And if we draw a line at 60 degrees based on the Korean data, most of the time the water temperature she recorded was above 60 degrees. So we started thinking, how could we provide cool water to these sows, make them comfortable, and maybe make them perform better? A project is born. We said, why can't we take solar PV, put it on a barn, use the solar to drive heat pumps and chillers to cool water. We'll take the cool water, we'll circulate it in pads underneath the sow so she can lay down on the pad in the farrowing stall, and then also pipe that cool water through the nipples to the sow. So we'll cool her from the outside laying on the floor, and will cool her from the inside by the water she's drinking. And so we've got, if you're familiar with Nguyen Manufacturing out of the Netherlands, they make this insert. Basically, you can plug in, this is the bottom side obviously, plug into that, circulate the cool water through that, and then she lays on this. And so that's the plan for this summer. We're funded to do that work. We've got the pads here from the Netherlands, and we're starting to retrofit to put them in. And we've got some engineering designs to see how we can make this all work. I am aware of some data out of Purdue that's done something similar, and that data will be presented in Omaha this next March, and at least anecdotally they're telling me there's some significant increases in feed intake in heat-stressed sows. So here's a case where maybe using that renewable energy, if you were going to buy it off the grid, do all that, maybe it wouldn't make sense to try to run this whole system, but if we can get power cheaper, and then we still got to figure out how we can use all that power in the wintertime that we'll be generating as well. And if we have time, we can talk more about the next step of projects that we have planned of how we capture the rejected heat from the sow.
Any idea what the cost for barrel crate?
Not yet. The inserts, you remember the inserts were, I think they were like $80? They were like $80 a piece for this piece here. Much less than I expected. And then, of course, we had to buy some other flooring to have it match and jimmy around. But so our plan is to do economics around it as well and run it, and how robust is the system and all those kinds of things. So the last thing I wanted to talk a little bit about was kind of the driver of all this is how do you reduce the carbon footprint of the production system, and how can you use that to satisfy downstream customers. And so Joel Tallickson is on our team that does life cycle analysis. And if you're not familiar with life cycle analysis, basically, and this is Joel's words, it's basically a counting system, trying to figure out what inputs come in, what carbon's generated from that, what are the outputs, where's the carbon going in the system. And you can do these life cycle analysis around water, around energy, around carbon, and so on and so forth. And there's a lot of factors that are considered: resource depletion, eutrophication, global warming. You can use water use. In the work in Morris, basically we're focusing on the amount of fossil energy that's used and the CO2 equivalents or greenhouse gas. The types of questions is, what's the base level of emissions and fossil fuel use in our system? So we have a kind of a benchmark to work from. How, if we make these improvements, how much does that move the needle on those emissions? And what production methods might have less environmental impacts? So basically, a whole bunch of calculations and all that. Behind this, I took a lot of Joel's work and condensed it down into one or two graphs. And basically, by Joel's calculations, if we look at pounds of CO2 equivalents per pound of live market pigs, so at the farm gate going off the farm, manure emissions are 0.77 pounds. Corn production is 0.65, soybean 0.14, and then everything else is 0.22. So everything else is what you're doing in the barn, transportation, heating, those kinds of things. Final number is 1.78 pounds of CO2 equivalents per pound of live pig marketed. And this is the conventional system at Morris without the solar panels, just what we would do in a normal production. We have been monitoring our finishing barn, our farrowing barns, the same way we did on the commercial farms, and making these calculations. We also have the crop production data from our farm as well. How does this compare? Well, corn production. If you look at this slide, you see the two biggest generators are manure and feed. And so Joel's done some calculations on conventional corn production. And basically in the corn production, the biggest chunks are drying the corn. This is CO2 equivalents, nitrogen fertilizer, and you notice that field work is significant but small. So tillage, harvesting operations, planting operations, those kind of things. So the opportunities of improvement are probably in these two areas. How does it compare to other places in the world? Basically, literature estimates here. The UK, 4.2 pounds of CO2 equivalents per pound of live market pig. The Danish system, organic base, 3.04. There's a number that you may have seen, 2.85. That would be the National Pork Board's summary that was done by, I've drawn his name, Toma at Arkansas a few years ago. Traditional Danish system and so forth down, and then here's our number, 1.78. So we look pretty good. But there's real caveats in these numbers. It's very difficult to measure or compare across because where do you draw the boundaries? Do you count processing? What conversions do you use? There's a lot of mathematical, hypothetical conversions and not things measured directly. So I throw this chart up just to show you that we're somewhere within the ballpark amongst other systems in the world. But is this the right number or is this the right number? Or it's going to depend on your system and also the way you make that estimation. So I think I'll wrap my portion up here and just summarize saying that market chains are going to continue to demand reduced carbon footprint, we think, and more environmental sustainability. And producers have tools that they can reduce fossil fuel use in some ways without compromising performance and animal comfort. And these changes, they're driven by consumer demands. Hopefully there'll be economic benefits to producers in the future as well. So a few acknowledgements. Our Swine team that helped collect data, Renewable Energy Group, you'll hear from Mike. Eric does a lot of the engineering work on solar. Kirsten, she's the one that gets to the farms and collects all the data. And I mentioned Joel in terms of doing the carbon footprint. Several other people. And then our funders that were really, this work wouldn't happen if it wasn't for their work. And Pork Board's been a part of that, and thank you producers for checkoff support.